Hi all, welcome to another edition of the Sigma Model Chronicles. I'm Vasu Sham and I'm joined again by Amr Ahmadain. Hello, Amr.
Hi, Vasa. How are you doing?
And good. So yeah, welcome back.
Thank
And
you.
today we're gonna dive straight into colliding local RG with the nonlinear Sigma model. The two
Yeah,
things we've been building up last time. And this is yeah this will kind of clarify sort of why we put so much time and emphasis on issues relating to the C theorem, understanding local RG with arbitrary background sources, and how it all comes together. And then next time we can jump to how that relates to off-shell string theory. So for now we can begin with the nonlinear sigma model. So you can take it away, Amr.
absolutely. Sounds like a plan. Thank you, Vasu, about this. Thanks. Sounds like a plan. So today we continue really our story about the local RG from the perspective of a curved will sheet with a dilettante.
Yes.
So what we have been saying so far about the Zimolodchikov C theorem is applicable to flat world sheets. So if you, in the context of string theory, sigma model, there'll be a flat world sheet without the dilettante and without the dilettante term, because the dilettante term has the Ricci scalar on it. So that is not part of the Zimolodchikov C theorem. So if you want to basically include or extend the C theorem, the two-dimensional C theorem by Zimolodchikov to string theory, we better reformulate or extend it to curved world sheets. And there, for example, if we're talking about the sphere, then we have the Ricci scalar and the curved world sheet, and then we can see where the dilettante factors into the story of the C function, and
Yep.
what the subtlety actually it brings about. And that was done in a paper shortly after Zimolodchikov's paper on C theorem by Arkady Tsetlin in 1987.
Okay.
That yes, that was done there, and maybe we can go a little bit through what the formulation is, what the problem is, what the dilettante and the curved will sheet do to the C theorem in string theory. But for that, let me to start, let me share my screen, and then we can get started. I
Wonderful.
wanted to start by a paper, and then we'll move into another paper as we go on. Yes, we'll probably start from this paper by S.P. de Alwas back again in 1988 when this was a hot topic, and
Mm-hmm.
people are publishing left and right about it. And so essentially, what this paper by de Alwas is trying to do is to argue that Tsetlin's formulation of the sphere effective action in terms of the central charge action and extending Zimolodchikov C theorem to include the dilettante and curved will sheet is actually there's something wrong about it, but it
Mm.
actually works, right?
Okay.
So actually that's what he says. That's what he basically the argument he gives here. He's not. We'll go through it. Doesn't have to. It doesn't have to be that what he's saying is completely is completely right.
Mm-hmm. Mm-hmm.
Actually, he gives the argument that it should work, and it actually works when he gives the reason why. Although, as again, and Aaron and I in the paper, we say that there's something wrong with the proof that he has
Mm-hmm.
here, and we discuss that in the paper. But again, so let's take it slowly. But it's a nice paper, nevertheless, to start with, and then because what he does in the first half of the paper is that he reviews this is just a quick review
Mm-hmm.
of the standard Samologica C theorem in a flat world sheet.
As
Right.
we did, as we did last time.
So,
Yeah.
right, because that's exactly what we did last time. Just a quick reminder. Right? Um, so here we go. And this is the three functions C, D, and E by which we use to construct the central charge, the central charge quantity, the central charge action, or the C function. In this case, which is C minus D minus 3E, right? And here is the conservation equation of the stress energy tensor. And the three functions C, D, and D are both functions of the coordinates x, in this case just x, and the couplings gi, at least in this notation here. The couplings are gi, and the x's, they're only functions of x and gi because we have two D Lorentz invariants, or Euclidean invariants in this case. Translation invariants as well will make the functions, these depend only on x and the couplings, right? Okay, so far, this is the story, and this remind you and the reader of this very important functions that this TZZ bar is using theta here, but we have been I think using TZZ bar is basically the sum over all the beta functions, or the number of couplings I, and times the associated vertex insertion or vertex operators, and that's and here is the C theorem, or the C function, right? And this implies, remember that the GIG, this object right here, right, is not the space-time metric, but rather a metric in RG space, a metric on the space of couplings, all right? I mean, coupling I and coupling J. And that this implies that there's an extremum of this object C, and at delta equals 0, since Gij is positive definite. So this guy is positive, and that is key for this thing to work, right? For this to work, is that we want to make the coupling Gi, this metric on the space of coupling, RG space, to be positive definite, and so that at the fixed point, right, when the beta functions vanish, delta IC equals 0, right? And if delta I equals C equals 0, that means C is sitting on an extremum, but it wouldn't be sitting on an extremum if Gij was not positive definite. That's the content of equation 7, right? And this is the statement of basically the C theorem in a nutshell, right, in equation 7. So the positive definiteness of the metric on the space of couplings is extremely crucial for this to work. And yes. And we also see something that I'm going to just give a hint for what is to come, maybe next episode or something. You notice that this quantity C, this C quantity, which is what we call the C function, right? The gradient of the C function on the right-hand side, you can see they're beta functions, right? So if we think of this C function as an action, this function as an action in target space, you see that the gradient of the action, so right now, equation 7, C is just a function, right? But if we think of this function as a local action in target space, what this is telling us that the gradient of the action on the right-hand side is a combination of some beta functions and a metric. And what we know that if the gradient of a local action is related to the equations of motion, and the equations of motion in string theory are beta functions. So this is crucial in the off-shell formulation by Arcadi-Zetlins. And this is what at least equation 7 is telling us, and this is going to become clear as we move along and include and discuss off-shell string theory. But this is just something to hint to what is to come. But let me get to the point of this, and sorry about that. And then we'll move to another paper. Up to now, and this is important. This is basically one of the few papers that, or maybe the only paper I'm aware of that makes this comparison very clear. Up to now, we have not really computed in the first part the two-dimensional in a 2D QT in a curved spacetime. So we haven't computed the stress energy tensor, right, in a curved spacetime in a renormalizable theory. In this case, spacetime for us, I should say, to be more precise, a curved world sheet. So we're doing string theory now, and we have a world sheet in mind with a background world sheet metric G alpha beta. Okay. And perhaps and then some couplings on the world sheet, tachyons, graviton, and some B mu. Just focus on the graviton for now. We can even throw away the tachyon for now and the B mu from the picture. Just we have a coupling which happens to be the G mu. Okay, so we have a curved world sheet with G alpha beta. And again, let me just, this is the world sheet metric. Right, and we can ignore all other couplings and just include G mu nu and as a function of x. And this is the space-time metric. Right. Good. We know, of course, you know, and I hope a lot of people know this from string theory, is that when we have a curved world sheet, we definitely have the extra term that's we add to the world sheet theory to make it consistent is the Dillon, right? So this is a term, this is D2Z, we work in ZZ bar coordinates, and then the R2 is the world sheet metric, and then the dilettante, right? That is a term that must be included in curved world sheet and to make the theory consistent. And this is the term that's going to play a major role in what is to come in the next few minutes in extending the logic of the C theorem to include the dilettante. So far, so good? Okay. So in the flat space limit, what is the flat space? Flat space limit is the limit where you take the curved world sheet metric, G alpha beta, to be flat. Right? That's what we call a flat space limit here. So the curved world sheet becomes a flat world sheet. Okay. Even then, the stress energy, if you were to compute the stress energy tensor of the dilettante, it would look like this. It would look like these are the two different. So theta ZZ would be delta phi squared, the second derivative or two derivatives of the dilettante, and theta ZZ bar. Let me remind you, I'm read also that this is basically the stress energy tensor in these complex coordinates. That would be T ZZ bar is like T, the trace of the stress energy tensor. Let me even do something quickly. One can verify this by going to this paper, this chapter 7. Again, let me remind you, this is chapter 7 of the Low Energy Effective Actions, lectures by David Tung on string theory. If you were to go to there's a particular page to convince yourself that this is actually something that is true, in the section where we discuss linear dilettante theory. Okay, so far so good. Okay, so here, this is basically to make the statement. So suppose I give you this beta function of the dilettante. So suppose I have a world sheet theory Okay, and we'll jump in guns a little bit, but suppose I have a world sheet theory and I have couplings, and one of the couplings is the dilettante, right? On a curved world sheet, as we just explained. Suppose I compute the one loop beta function. The one loop beta function will look like this, right? And well, it's not surprising that the beta function of the dilettante looks like equations of motion. I mean, maybe you haven't emphasized this. Now we're getting into the territory of sigma models and string theory. And this is going something I promise we're going to get into in great detail. But the beta function of the dilettante, all other couplings, they look like equations of motion, equations of some action, and this action happens to be this guy.
Yeah.
So if I were to give you this action in target space, right? This action in target space in d-dimensional target space, and I ask you to derive the equations of motion for the dilettante, you would end up with 728, which is the beta function that you would derive from the world sheet theory using whatever techniques you like. Dimrev plus minimal subtraction scheme, do something. So I give you a world sheet theory, ask you to derive the beta function for the coupling. I end up with equations of motion of some action in target space. Weird connection between a two-dimensional sigma model theory on a curved world sheet and target space effective actions to some order in alpha prime.
Yes.
Where the beta functions mysteriously appear as equations of motion of some action. That connection between the beta functions of some sigma model, two-dimensional sigma model on a curved world sheet, and effective action and equations of motion of some effective actions, that connection is made very, very solid and very concrete by Zeppelin's formalism.
Right.
That is one of the powers of that, and this is why we're interested in improving it and making sure it actually works. But that connection is what we're going to talk about it in a lot more detail later on. But this is again something just observed here.
Yeah, well, I mean, another thing that was touched upon in the very first episode in the series having to do with the local RG of two-dimensional theories is that in the local RG equation, there's going to be a term that at the fixed point would become the pure anomaly term, right? And that's the anomaly in two dimensions proportional to the Ricci scalar. Away from the fixed point, that thing is going to have prefactor that depends on the couplings. And that's the beta function for the dilettante. Right, that's the beta phi term multiplying r, and it's clear from the derivation we had back then that this plays a very non-trivial role. And it's the subtlety is when we're after situations, like as we will discuss, is when we're after situations where we want the central charge itself to vanish, right? And that's when we need to pay close heed to what's going on with this term.
Yes, absolutely. And this is the problem where the dilettante is actually going to introduce. You actually beat me to it. This is the problem that was cited and noted by the Alquist. And so good. So that's exactly related precisely to that problem. And I just wanted to mention that, good. The beta function of the dilettante and the beta function of any renormalizable coupling on the world sheet will appear as equations of motion of some target space effective action. And you can see this mysterious connection between target space and target space effective actions and two-dimensional world sheet theories, sigma models. It's just one of the most beautiful and connections that was, I think, maybe unraveled, discovered in the 80s during that time where conformal field theory techniques and sigma model techniques were being developed for string theory and the like. And that's at the heart of what we're going to talk about. But suppose now I turn off, and going back to the statement by T. Always, right? We want to make sure that even in the flat space, that's the statement that's why I switched to the lecture notes. is even in the flat space limit, when you send the curved world sheet metric to flat space, being from G alpha beta to D, when we send it to, this is the world sheet metric to the alpha beta. If you have a dilaton term, the stress energy tensor of the dilaton is not zero. So let me,
Right.
this is this statement. So suppose I would like to get a solution for this equation of motion. I'm going to turn off all the other, so I'm going to turn off the H unit fields, going to turn off everything else. And I'm going to focus on solution to the equation 728, which comes down to solving this equation. All right. And of course, the linear dilaton conformal field theory, and the linear dilaton mean just, this is one of the most important and exciting topics in string theory, and touches on many different areas, and Liouville field theory, Liouville sine-Liouville theories, and walls, and linear dilaton. This is just very important. And this is basically the starting point. Maybe this is the intuitive way to understand what a linear dilaton is. So you start from a beta function of a dilaton. You just look for equations of motion for this innocently looking right? Solutions for this innocent looking equation of motion. Purely simple. What you find is that if you work in a specific signature in target space, of course, that 20 and then that you look for solutions. Well, the solution is going to be the following. Solution is going to include is either going to be space-like or time-like, depending on whether the dilaton lives in d less than 26 dimensions or d greater than 26 dimensions. And this is, again, because of this signature right here. So you see here, it's only linear. So it's going to have, when I say space-like dilaton, means it's going to have a space-like profile. And that's because d less than 26 will make this term on the right-hand side positive. And when d is less than 26, the right-hand side is positive, and due to the signature, space-time signature, this is going to have a space-like profile. And equivalently, if it's greater, then it's going to have a time-like profile, and it's going to be, so we call this a non-critical string theory. So it's just weird, because we learned in string theory that one of the first things we want to cancel the anomaly, and one of the cancellation of the anomalies is what requires c equals 26, and we add the ghosts, and we have c equals 0, and this is what we define a conformal field theory that describes strings to be, is a c equals 0. The interesting part about this is that no, we can have strings propagating or living in d not equal to 26 in this particular interesting case where the dilaton is only linear in one spatial or temporal direction, right? We can have a consistent definition of string theory in this kind of linear dilaton backgrounds. The conformal field theory is exact to all orders of alpha prime, and therefore it tells us, and we can definitely analyze a lot and study a lot and learn a lot about the string theory in this case, linear dilaton. Right?
It's fascinating because it's consistent, and at the same time, we've had to truncate to only the dilaton to make this work, right?
Yeah.
In terms of the fields, which means that like these are weird string theories that are kind of inert when it comes to their excitations having to do with like whatever.
Absolutely.
Even the graviton, the F1s, there's none of that.
Yeah.
Very, very
yeah, it's inert. Exactly. All of these other excitations by other fields, precisely. And nevertheless, they're very important, and they show up, of course, as you very well know, in different applications, different areas in theory, in different very important applications. So coming back, so suppose I have this term on the world sheet. So let me remind, this is a world sheet term, right? Because here I have d2 sigma, which is d2 z, and then square root of g. This is the square root of the determinant of the world sheet metric, and I have my dilaton as a function of x being the space-time coordinates. Reach our superscript 2 is the Ricci scalar on the world sheet, right? So suppose I have a world sheet theory that is curved. So the world sheet is curved. I'll have to add this term as I explained. Now let's compute the stress energy tensor. As we know, the stress energy tensor is going to be taking the derivative of the action, space-time action, S, this action right there, with respect to the world sheet metric, and then take the limit as G alpha beta. Let's take the limit as G alpha beta goes to flat. This is what the owl was actually meant by taking the flat word sheet limit, flat metric limit. So it's obvious, right? Because if I have a flat world sheet, then this term is 0. Because R2 is 0 on a flat world sheet. This is not surprising. However, what we're going to see is that although this term vanishes on a flat world sheet, the stress energy tensor does not. And this is exactly the way to show it. So you compute this on a curved world sheet and take the limit as G alpha beta becomes delta alpha beta. And when you compute the variation, what you're going to end up getting is this stress energy tensor looks like this. And it's not traceless. It's not traceless. And when we have something that is not traceless, that means that trace is not 0. And so far, I hope this has been obvious that we break file invariance, right? Because the trace is not 0. Good. So we break file invariance, but that we know because adding the dilettante term in string theory at the classical level breaks file invariance. It's only at quantum level that things are recovered, that the file invariance is recovered, right? This is something we know. And so, yes, classically, as we can see, this thing is not traceless. And in complex coordinates, this is what it looks like. So it does not vanish. And notice that here we have delta alpha beta, not G alpha beta. So we have already restricted the flat space in this equation. Already there. We have restricted the flat space here in this equation. And we see that it does not vanish after taking the flat space limit. And this is interesting. I'm not going to get into linear dilettante at this point, OPEs and what does this do to the central charge. It's not the point, but the point is to show that even though the dilettante term vanishes in on a flat world sheet in 729, the stress energy tensor in the flat limit does not, and it's actually given by this equation right there in the box. Good. So far, so good. Okay. So let's go back to our story and the comment that was given here. Now, the renormalization group equation, the Kellen semantic equation, is given by this in general without the dilettante. So let's do this. Without the dilettante on a flat world sheet where there are no dilettante, there's no dilettante coupling, there's no beta function, I would not have this term, right? So that will be the renormalization growth equation, right? Here, the sum is over as usual, all the beta functions, and G's are the couplings, and so on. So good. But now, if I have a dilettante, then I'll have to add the beta function of the dilettante. So here in equation 9, I is the sum over all the couplings, not including the dilettante, because the dilettante is explicitly included in its own term. Good, good. So let's see what this does. Okay. As we mentioned before, on a curved world sheet, we have this beta R2 term. So if we want to take the C theorem and talk about the C function that we would get from equation 9, after we have taken the flat space limit, it will come down to equation 10. And you see equation 10, right, has beta I, delta, the derivative or the gradient of the C function, which we said in string theory that would be the action in target space. Taking the derivative of this, the gradient with respect to the coupling, beta I here represents all couplings, and beta phi, and then we get the delta beta I beta j g I j. This is basically the C theorem of Samologikov extended to curved world sheets and includes the dilettante. So, right? So this is the C theorem on curved world sheets when including dilettante. Okay. What is a fixed point? Well, a fixed point, as we've defined it I think last time, and you've done it before, if you've defined it before, is where the beta functions vanish. Where the beta functions vanish. This is where defined because the beta functions vanish. You have a fixed point and you have a conformal field here. You recover violin invariance again. And then use the positive definiteness of the Gij to imply that scale invariance implies conformal invariance, because there's a subtle difference between scale invariance and conformal invariance, right? You can have, well, let's get into that. We'll get us into, yeah. Okay, so here scale invariance implies conformal invariance, which is a pretty, I think, statement that is well known and trusted. So then it follows from conformal perturbation theory argument. So when here we're doing conformal perturbation theory in the sense that you're doing your quantum field theory is a perturbation around a conformal field here, string theory conformal CFT. And that's conformal perturbation theory. This is basically where the direction or the proof that Aaron and I taken on paper. So this is conformal perturbation theory here. It implies that beta I equals 0 for all couplings, and the dilettante beta functions. So if they were to vanish from the world sheet perspective, or vanish, we're at a fixed point. This implies that the by positivity of the RG metric, that delta I equals delta phi. That means that the gradient of, let me read this out, the gradient of the C function with respect to couplings Gi is equal to the gradient of the C function with respect to dilettante, right, is equal to 0. So the beta functions,
right,
the vanishing of the beta functions, now we're talking string theory, the vanishing of the beta functions on the world sheet theory implies that in target space, you are sitting at a minimum.
yep,
An action or a minimum or extremum. In other words, if you have a conformal field theory, this goes like this, implies that in target space, you're sitting at a string vacuum. That is extremized. So this means that your string theory action in target space is extremized, which is what, so you have a stable, let me be a bit more, this is a string theory stable vacuum.
Yep.
You're a stable vacuum, you're sitting at an extremum, and usually a minimum, second derivative, and you are at a stable vacuum. So that's good. Why is that bad? You can ask, why is this important? Well, because it doesn't make sense to say that if I have a conformal field theory, if I'm at a fixed point in my RG flow, defined by the vanishing of the beta functions, and defined by divided invariance, conformal invariance, to be precise, that in a string theory context, this would correspond to a gradient of an action that is not sitting at a minimum, or it's not in extremum. Basically, what we're saying is that this would not solve the equations of motion of a particular target space effective action. As we've mentioned before, and again, we're going to get into this later, that the beta function, the vanishing of the beta functions correspond to some solution of the equation of motion in some target space effective action. Will this tell you, if this was not true, this means I'm sitting at a fixed point where at a CFT, but this does not correspond to a solution of the equation of motion of the target space action, which is crazy. Something is wrong. This must correspond to that. Okay. And again, this is one of the things that we do in our paper in detail, that error. But you can ask, does this imply, and this is now going to get into a little bit of that, this imply that the other direction is true? Does this imply that if I have a string vacuum,
Right,
this implies the other direction as well? So does this imply this? Does this imply this?
yes, that's the question. Yeah.
Right? Does it automatically imply one direction, a CFT and a string vacuum implies that the string it tells you something about that if you are sitting in a string vacuum, that this corresponds to a CFT on the worksheet. So that's the question, which is the converse statement, is true, and this is where the dileton is going to become important, only to the extent that delta I, that means the gradient of the C function equals 0, and that delta phi is equal to 0 implies that
The beta bar is a 0, yeah.
Right. So far I haven't really talked about the beta bars, but because Zetlin talks about the difference between. Let's get into that a little bit maybe later
Sure.
today. Difference between, as Vasu pointed out, here I've been using betas just without any other qualifications of bars or twiddles and top. But as a matter of fact, in Zetlin's formalism, of course, there is the beta function has a little bit of bar on it, as a bar and twiddle on it, and there's a slight difference between that beta function, these beta functions, and the beta functions with bars or twiddles on them, beta I. So we're going to get into that at some point. But here's the thing: what Zetlin argued in his paper, published a little bit after is that that delta phi c, that the derivation, the derivative or the gradient of the C function with respect to dileton does not just imply that the beta functions of all couplings vanish, but rather that the beta function of the dileton also vanishes.
Mm-hmm.
Right. And if you before I get into this a little bit, let me remind you that the zeroth order term in the beta function of the dileton, the zeroth order term in the beta function of the dileton
is d minus 26.
Is d minus 26, which is the central char. Right. So that term is part of the beta function. So you can ask, but then you can ask, does this also going to vanish? What Alois is saying is that Zetlin pointed out in his extension of the Molodchikov-C theorem to string theory, curved worldsheets, is that the gradient, if the gradient of the C function with respect to the dileton would imply then the beta function of the dileton would vanish, which basically means that d minus 26 is 0. So there's no central char. Here we're talking without even the ghosts.
Yes.
We haven't added the ghost factory yet. Remember, so you can ask, okay, but that's known. Okay, of course, D minus 26, we know that any CFT that describes string theory or strings must have C equals 0. But here what we're talking about is that the D minus 26 will vanish before we even add the ghost sector to actually make it vanish.
Right.
So any CFT that so if this were to be true, any CFT that according to the C theorem extended to string theory is that at the fixed point, any CFT that describes string would have a 0 central charge. Let us go through this a little bit, and to make sure it's kind of clear.
Right.
Remember
So
that,
just exactly, just to like
yes,
clarify what the implications are, right? So first, I
please.
guess the implications going back from the boxed equation down there is, starting with 9, what we're doing is we're asking about criticality condition, which is like if you go down, so we're saying that if the beta functions vanish, right, then
Yeah.
the positive definite, so beta functions being beta I, beta phi, if they vanish, then the positive definiteness of G will require that beta bar I, beta bar J also have to vanish, right?
Yes. Yes.
And then we're basically saying that, well, given that, you conclude that, well, then we want to make a statement about the gradients of C, right?
Yeah.
Which is the next thing to understand, because what we have right now is just statements about the vanishing of various things. Now, of course, what we want to do is associate C with some kind of target space action. And so the vanishing of the gradient of C is the condition that we're on a solution of the equations of motion of the target space.
Yes.
So what we want to do is
Absolutely.
then draw an arrow backwards. Given we've done that, what's required, right? So you want
Yes.
to know, to what extent does the gradient of C with respect to the couplings and with respect to the dilettante vanishing mean that beta bar I has to vanish, right? Because we went in one direction, now I want to go in the other direction. And this is where the question about what's going on with the dilettante's beta function also comes in, basically, right? Because it's one of the couplings, so we need to know.
Yes. Yes, absolutely. Absolutely. It's one of the couplings. You cannot just ignore it, right? It's one of the couplings, as you just rightly said. It's one of the couplings. So we want to know what the implications of having it vanish mean, right? If we just let it vanish. And this is the weird thing that we're going to say. So let us define uh, let us define if all the couplings right. So suppose all the beta functions. Suppose and just to make sure that suppose we only have the graviton, right? The space-time metric, which is the graviton in the world tree. Suppose I have just the beta functions of G vanish. So suppose that beta G mu nu vanish. And I want to define this as my conformal point. So before I include the dilettante, let's define this as the conformal point. So all the other couplings, well, here I'm just I restricted myself for simplicity to the graviton beta function. Suppose it's just 0, right? Conformal point. We define this as the conformal. Without the dilettante, I can define this as the conformal point, right? And suppose I am at one of these points. So I am at a conformal point where the beta function of the metric is 0, right? Then by definition, as we just explained, that the beta function of my dilettante, and suppose we're doing constant. So suppose we're considering solutions with constant dilettantes, right? So all the terms with which involve derivatives of the dilettante, 0. Fine. Suppose we're only interested in these ones. So then what is the remaining? The remaining part would be D minus 26. So if this were to vanish, so then, and this is, we know, is the central charge. This is the central charge, right? And basically there's maybe a factor of 6 here or something, but this is the central charge of your CFT. string theory CFT would have this central charge. D minus 1 is equal to the central charge. So requiring that beta functions of the dilettante to vanish at fixed points would necessarily imply, well, that the CFTs that describe strings would have a vanishing central charge. They're not allowed to have. This is what the implication would be. And this comes from noticing the following interesting calculation. So let's start from this, but let's start from this. And well, it's actually even simpler than so maybe I'll just explain one little point before I do this. The equation of, so suppose I give an action in target space that looks like integral d dx square root of the space-time metric, and we know that we have this space-time effective action. We have this function here, e to the minus 2y, right? And then I have some Lagrangian density. But this Lagrangian density is going to be functions of the gradients of phi and other fields. Right away, your Lagrangian, the only term in this action I that has a term, the only term that does not have a derivative of phi is that term sitting outside.
Right, that's the only contribution to the variation that comes with no derivatives of phi.
Absolutely right. So this term, there's no other term in here that depends on phi. All the terms in the Lagrangian density depends on gradients of phi. So that means we know from quantum mechanics, the symmetry under translation of phi in target space. That symmetry that you have of the effective action in phi implies that the equation of motion of phi will be a total derivative term. Well, as a matter of fact, will be proportional to the action itself.
Right, right.
As a matter of fact, because of the consequence of the symmetry, and this is in general, but it happens to be very important in here. What we're saying is that minus 2 e to the minus 2 phi.
Well, basically, if you can shift phi by something constant, then the gradients don't care, and you can just redefine phi in the exponent.
Absolutely.
So at that cost, you just have, yeah.
Yes. I think if e to the minus 2 phi times the Lagrangian is equal to delta mu times the functional derivative of the Lagrangian with respect to delta mu phi.
Yes.
Is that right?
I think so, because basically what we're playing off of
Did
is
I make a mistake? Maybe there's a minus 2 here.
Yeah, so you could do like constant rescaling of G, compensate that with the rescaling of phi. And within the Lagrangian, if there are only gradients, then the shift of phi does nothing. And so that's the action of the symmetry, and you would have to take the variation of the action under that symmetry. And since that involves both, well, it involves both this simultaneous thing with G and phi, the net effect will take the following form because okay, so it's a noether theorem exercise.
Exactly right. Even without exactly, it's just a symmetry in phi. It's a constant shift in phi in target space that implies that the Lagrangian does not depend on phi directly right here, and therefore you have a symmetry, and therefore your equation of motion for the dilettante is going to be a total derivative term.
Right.
And that total derivative term, it's a little bit maybe is important because we say that the sphere partition function on shell in string theory in asymptotically flat spacetimes is a total derivative term.
Mm-hmm.
Let me repeat it again. The on-shell action, the tree level of the sphere in asymptotically flat spacetimes is a boundary term. And this boundary
Yes.
term can be reformulated as a normal derivative and ultimately will take the form of d minus 1
Mm-hmm.
x, the boundary metric,
Mm-hmm.
h, the normal derivative of the trace of the extrinsic curvature tensor times the dilaton.
Yes, yes, yes. So I mean,
Ultimately,
just
it can be massaged into this form. So it
right.
includes the Gibbons-Hawking boundary term. So the Gibbons-Hawking boundary term of the sphere partition function, is a boundary term, comes from the fact that the partition function, that the equation of motion of the dilaton is proportional to the action. It vanishes on shell, right? It vanishes modulo of the total derivative term, right?
Yes.
So if you're on shell, the equations of motion are satisfied. You're zero. So the dilaton by this is zero. Modulo this guy. So in non-compact conformal field theories, I can forget about in compact field theories, in compact space times. If I forget about the right-hand side, I don't have a total derivative term. Then I'll have okay. Then the bulk term vanishes, which is what I mean by that. But the fact that it just vanishes. But if you have a non-compact target space, then you would be left with a boundary term. Comes from the fact that this constant scaling of the symmetry of the constant scaling of the phi, and this is, we do not have a world sheet derivation residue of this since you and I have
Mm-hmm.
been
Yeah, we've been talking a lot
about this.
about that. Yeah. Mm-hmm.
Um, okay, so we don't have world sheet derivation of this term at least in this form that includes the Gibbons-Hawking term. Maybe there's other boundary terms that we can find if we were to derive it. But let me just point this out. And by the way, this is going to be related to the statement that on the world sheet, the partition function vanishes because of the infinite volume of the conformal thing. This is the
Mm-hmm.
space-time naively, the space-time manifestation of the statement that the sphere partition function vanishes on shell due to the volume by the infinite volume of this LTC. And this is why
Yes,
people
yes.
believe
No,
that this statement is true to all orders in alpha plane
yeah, we should
because of this
really
connection.
qualify that. Yeah, because it's very important because
Yeah.
that's indeed the origin of it. And again, just to go over that again, like this is an exercise people really should do. Like what we're thinking of is varying with respect to the trace variation with respect to the metric, varying with respect to the dilaton, and varying the Lagrangian with respect to the dilaton. There are the three things going on. There's a two because the effect of varying with respect to the metric is like minus the effect of varying with respect to the dilaton in the first part, right? Where it's like the overall volume. And then the variation of the Lagrangian just involves variation with respect to derivatives. And then what's going to happen is that you're going to have a variation, the derivative of the variation of phi. And then you integrate by parts and you get that to come out the other side. And so that's essentially how you get this this relation. And I mean, it's a sort of very simple, innocuous looking thing, but it answers the question of how can it be that the thing we think of as the action vanishes on solutions? Well, this is how, right? It's just it's as clear as
In
this.
string
You're
theory, this is the
maintaining the symmetry.
peculiarity of, yes, yes,
It's the cost of just maintain that symmetry. This is what's going to happen.
yes, absolutely. It is because of this constant scaling of the phi in target space, and the fact that e to the 2 minus 2 pi is the only term that's sitting outside, and there's nothing else in the Lagrangian that depends on pi except depends directly on the dilaton, is what makes this whole thing interesting, I would say. And what this is saying is that now if let's go back to 12, suppose I'm at a fixed conformal point where the beta function of the metric vanishes, I'm only left with the beta function of the dilaton. So basically you eliminate, since by definition you eliminate that term because the beta function just vanishes. And if you were to write down, yeah, we consider the yeah, exactly here beta I equals 0. if you were to write out that term explicitly, this is basically the exercise I was just telling you about. You end up with a statement that here's equation 13, right? That the right hand side, right, delta c delta phi I delta d dy is going to be equivalent. It's going to be proportional to minus 2 times the action. This is basically the action, right? Minus 2 times c here is the action. Here we just call it the c function, but this is really minus 2 times the action. This is what we just wrote basically here. E to the 2 minus 2 phi times the action is minus 2 times the action, because this is the action.
And again, like another way to see this is in the old sort of like derivation, you know, like Osborne style derivation of the C theorem, the strong C theorem. You notice that the object whose gradient is driving the RG flow is the coefficient of the Ricci scalar in the local RG equation, which is why the C function ends up being the action. Like it's again, going back to that, it's a very sort of clear picture. Like that had to be your answer in some sense.
Absolutely. That's and as we're going to point out maybe now is that in Zetlin's formalism, the trace of the stress energy tensor takes the form, if you compute it explicitly on a two-dimensional stable model off shell theory, will take the form of a beta function. I'm going to put the dilaton without defining it for this twiddle times this Ricci scalar. I mean the leading order term times the Ricci scalar of this. So this is very reminiscent of the central charge, because in a CFT the central charge is just C times R2. So this is an explicit calculation. The beta function, this twiddle phi, which includes the graviton and the dilaton, appears as the coefficient of the Ricci scalar on the world sheet, which means it's the anomaly. It is the trace anomaly, trace coefficient, and that's why it derives RG flow. That's why. But at the conformal point, what we're saying here is that at a conformal point, where the beta g vanishes, this includes beta g and beta phi, this object in the twiddle. So if I were to write this out explicitly, so what we're saying is that if I have this, suppose, and I have beta g mu nu times g mu nu, something like there's a factor of -4, and then I'll have beta phi. This is the dilaton part. And then if I were sitting at a conformal point where I assume that the beta function is 0, then I'm left with beta phi. And right? And
you mean like beta phi R or
beta phi times R.
Yeah.
Beta phi times R2. And if I am interested in constant dilatons, then this would definitely be d minus 26, which is the central charge, times R2. In Zetlin, there's, I think, a factor of, it doesn't really matter at this point. So see, this is the leading order term. There's another, is the scheme dependent term that comes after that, but this is the important point. The trace of the stress energy tensor, the expectation value of the trace at a conformal point, comes to be the central charge d minus 26 times R2. So now if you're sitting at a fixed point, and now look at this equation 13. Since we are assuming that this is the C function, this is our C function, so basically beta i's are 0 because we are at a conformal point, so this also is 0. You're left with beta phi delta phi I. Now take the derivative. This is an action. Take the derivative with respect to the dilaton of your action, right? Of your central charge action, you would get equation 13. But now, as we just worked out, the equation of motion of the dilaton is proportional to the action itself, right? So if the beta function on the left-hand side of equation 13 vanishes, what we are saying that on the right-hand side, your central charge minus 2c will vanish, because we just said that at a conformal fixed point, this going to be equal to 2 minus 2d minus 26, basically. Okay, so if my beta function of the dilaton vanishes, if just like any other beta function of a coupling, this is as a consequence of what Setlin actually told us. If at a fixed point the beta function of the dilaton were to vanish at a conformal point, then with this, because of this conformal symmetry that we just discussed, this would require us to conclude that at a fixed point the central charge itself must be zero. Yep. This means that this is going to be zero, and that d, therefore, is equal to 26. And this means the conclusion that at a fixed point, all the conformal field theories describing string theory must have vanishing central charge before you add the ghost sector.
Right. And this is just...
And this is really stringent. Yeah.
We have to be we have to qualify what we mean by conformal point here. Is that it's different from what we would think of as conformal field theories in the wild. Like, certainly you can have two-dimensional conformal field theories of whatever central charge you like. And from the perspective of what's going on here, they wouldn't qualify string backgrounds because they don't actually have Weil invariants. They're all anomalous, right? From the perspective of this requirement, they're all anomalous. They're going to have non-trivial terms. So once you couple them to curved background, you're going to see that beta phi term. That's all they're going to have, but you're going to see that, right? That's their definitional statement. That's the fixed point statement. And so in like in the yellow book, all those conformal field theories, they're all coming with this R2 term if you were to put them on a curved background. Right? And that's fine. And you see that it's like, you see it on flat space when you look at 2-point functions, the stress tensor OPE alternatively. But if you really wanted Weil invariance, right, then it has to be that term vanishes, which also means that it has to be, or rather, we're seeing that it has to be that term also vanishes. Right? That's kind of the consequence of what we're saying. It didn't have to be like that in principle. There might still have been a possibility for you to have had something happening differently. But what happens is that there's this object appearing in multiple places playing different roles, right? This beta phi thing. It's appearing in the RG equation. Yes. It's intimately related to the thing that appears as the potential that's driving the gradients, right? So because of these interlinking, because of these multiple roles, you have relations like the one that you've outlined here, right? And that's why C has to vanish. So that yes. I think is like, it's great to see it just from this RG perspective, where we haven't done anything with ghosts. We haven't even made any considerations of what kinds of fields these are. We don't know. We don't know what the fundamental fields are at all here, right?
No, nothing. This is a very abstract statement, a very general statement about give me a sigma model, these common couplings on the world sheet, require that all the beta functions vanish at a fixed point. And if you require the dilaton beta function to vanish, then you would require that the conformal field theory would have zero central charge, before adding the ghost sector, even before adding the ghost sector. And this is maybe the too stringent, too restrictive, right? Mm-hmm. Because as you just mentioned, coupling to a curved in just two-dimensional conformal field theory that we'll look in the book, like in the yellow book or something, coupling to a fixed curved background will introduce the curvature, an extra scale, the scale of the curved background, and this will show up in the trace of the stress energy tensor under a local Weil transformation. And this will, so quantum mechanically, we say the Weil anomaly is broken. Quantum mechanically, the Weil anomaly is broken due to coupling to curved background. And the way it shows up in the stress energy tensor. You would have the central charge of the theory times R, and then you say, okay, well, this reflects Weil invariance. This is true in string theory, right? Quantum mechanically, we also have it. We also have this Weil anomaly, and because of the dilaton and everything. And the way we do it is that we say if we have shows up in the calculation as C equals minus 26, right? And this is the leading term in the beta function of the tachyon. So on the dilaton, you have other terms, but if you don't have anything else, you just have the C minus 26, and we say, okay, then we add a ghost sector. I make the Weil anomaly vanish quantum mechanically, right? And then I have a C equals here conformal field theory that defines a consistent string background, right?
Yes.
So that's the usual story. And how to cancel the Weil anomaly, and the leading order being C minus 26. What we're learning here is that what we learn in Polchinski, for example, is this D minus 26 term, which it defines a central charge, and then because of which we add the ghost sector, appears as the leading order term of the beta function of the tachyon.
Yep. No, the
That's
delta.
what we're learning from here. But the point is, requiring this to vanish, requiring that all the conformal field theories that describe string theories to vanish, to have zero central charge before I add any ghost sector is extremely restrictive, right?
Yes.
I mean, this is the content of this thing. But before I add anything else, saying any CFT would have to have zero central charge, right? I mean, and this is
yes.
This is basically the content of here, that it cannot be made flat, right? You cannot make a sphere flat, right? But on the torus, you would not have any problem, for example, right?
Yeah.
And so this is the condition here that we're saying is very restrictive. So because we know there are conformal field theories have central charges, right?
Right.
But then he goes on to try to show that nevertheless, it's true. It is true. I'm not going to go the argument now because it needs some machinery, but I'll point out that there's something wrong with the argument because it involves translation invariance on positivity on the sphere, which is not true. So
right.
let's reflection positivity on the sphere. The proof. So although he points out this inconsistency in Setlin's C theorem,
yes.
So semological extent, he moves on to say in the last part of the paper that nevertheless it's actually correct and it's right and it's valid, but the way he shows it's valid, the proof that he gives that it's wrong, it's just it involves reflection positivity on the sphere and it's wrong and so forth. So for that we have our paper to look at and a forthcoming paper. And forthcoming paper that we're going to expand on the C theorem part on the sphere.
Right.
In a separate. So good. So now we learn what the difficulties are of including the dilaton, curved Reuel sheets, the relationship, the dilaton equation of motion, and the boundary term, and this very interesting thing that makes string theory special. This constant scaling symmetry and the constant rescaling of phi, which makes the dilaton equation of motion be proportional to the action, and the vanishes on shell modulo a boundary term, which happens to be related, which happens to include the Gibbons-Hawking boundary term, but maybe other boundary terms as well, and which we do not have a consistent world sheet derivation of until today. But that's to make a story short. Now, if I switch quickly in the last few minutes to something else, I wanted to touch on the paper by Arkady Zetlin.
Yes.
It's a fairly recent paper compared to 1985 and
sure, yeah.
The 2007. So 14 or 15 years ago, where, in my opinion, he has a very nice summary of his work on sigma models and central charge action and the relation to the sphere partition function, right? So far, we haven't explained, or maybe just hinted to, how the story is linked to off-shell string theory and the sphere partition function, right? But again, I'm going to say one more thing again, that the sphere action, the classical tree-level sphere effective action, takes the form of a central charge action that we just described by virtue of some unique field G definitions. So this is all the story is very relevant to off-shell string theory, and it's in particular the sphere action, because the sphere action takes the form of a central charge action in Setlin's formalism, and that's why it's relevant. We haven't really discussed in detail the other side of the story, starting from the sphere path integral, but we will.
Okay. Yes.
And so let us, before I end with, I want to mention 2 points before I end today's, but we'll come back to it later. It doesn't have to be a shortcut. Maybe
Sure,
we can
sure.
come back to
Yeah.
the RG story in Perelman's entropy here, because there's a
Yes,
story about
that's a
Perelman's entropy here.
yeah.
Um, and how it relates to that. But let me point out that so far I've hinted at this, that the beta functions really show up in when you calculate the trace of the stress energy tensor of a sigma model that is a deformation away from flat space-time. So this is what basically Zeppelin does. His sigma models, his quantum field theories, or sigma models in the world sheet are deformations, slight deformation away from flat space vacuum, right? From flat space, from a flat metric and a constant dilaton and b mu equals 0, right? When you compute the beta functions using DIMRAG and using I think minimal subtraction scheme, which is because they love one another, right? As an RG scheme, you find that the beta functions are called the Weil anomaly coefficients. These
Yes.
Weil anomaly coefficients. So first of all, it takes this form. This is the operator form of the Weil anomaly, right? This is an off-shell statement because it's an operator form, which is an operator form, which is what we mean. It holds off shell. It doesn't have to hold on shell. It holds off shell. That's what I mean by operator form of the trace anomaly, the two-dimensional. It come to this. You see that you have a beta function, the beta function of the metric. Here I'm setting the b mu fields to 0. You can add it. The beta function of the metric, and then the usual term in the vertex operator,
Yes.
and then you have R2, and then you have the beta function of the dilaton.
And just
But
for
notice that
just for
yeah,
clarity, this is the format that Osborne lays out for what the local RG, like general local RG flow equations for two-dimensional theories looks like, right? This is the beta O minus like R2 times big C of phi, he calls it. There's a big C
yes,
is just,
yes,
and as we saw, like the difference in
yes. I
what
think
the beta functions are for the purpose of that equation versus the beta functions that one can compute, say some other way, will be things that differ by total derivative terms, right? At first sight, they have this total derivative character to them, that what you're adding is like these d mu, like these diffeomorphism terms, and then as you can see, mu itself is total derivative. So those are the kinds of like changes between essentially schemes that one needs to account for in order to put everything into this format 2.3. Because in principle,
Yes,
we could have broken that, as in we could have just chosen a different format, but the relation will involve essentially these field redefinitions, which I guess you'll get into.
yes, exactly. That's exactly right. What I wanted to mention and is that exactly, well, the difference between the beta functions with a bar and the beta functions without a bar, which you can always also calculate using different schemes. So I think Zetlin calls this these are Weil anomaly coefficients, and these are scale anomaly coefficients, basically. The one without in his original paper, 1987, is that these are Weil anomaly coefficients, and these are scale anomaly coefficients. And the difference comes in is that because in the derivation, which maybe we can get into, we can, but it's very detailed and technical, is that these extra terms, and here's the definition of, so del mu, these are this covariant terms, look, covariant derivatives of mu, so looks something like a current, like
Yes,
f
yes.
mu, right? Basically
Yeah.
like del, except that this is of course plus, not a sign, but it looks very much like f mu, except again,
Yeah.
this is
Up
symmetrized
to the
with
sign.
anti-symmetrized. And here's mu, and this is just some covariant vector that is you can construct from covariant derivatives. And again, here's some examples, explicit examples of what mu looks like and w looks like. Again,
Yeah.
here. So there are really some total derivative terms. And here's what it looks like. And so let me put this into focus right here to just make sure that we get the full picture. So what are we talking about? We're talking about deriving the beta functions from the 2D sigma model using dim-reg and minimal subtraction scheme, as was done back in the days. Now, what you'll notice is that you can add these extra terms. These are total derivative terms. So mu, w mu g. So you see this is just the gradient of the dilettante. And in the minimal subtraction scheme, you see that this w mu will be non-zero starting at alpha prime to the third, which is interesting.
Yes.
A three-loop coefficient, and it has been calculated in several papers, and I've looked into these papers by the authors. They have calculated three-loop coefficients and the four-loop coefficients, when it comes to equations of motion, when it comes to defining beta functions as equations of motion of a target space action, although it's beta bar, we should use beta bar, we're actually using beta. We're throwing this out at least to first order and alpha prime. We're assuming that, for example, delta mu g will not contribute, and that there always exists an RG scheme whereby we can set these extra bits of these extra terms up to zero.
Yes.
And there always is such a scheme, and therefore we say, okay, the beta bar is just like the beta function without the bar.
Right.
And that's the rationale that when it comes to defining the beta functions as equations of motion of target space of off-shell actions, we don't use the bar.
Right.
But they're important. They're very important. They're they're diffeomorphism terms. And maybe they do something important because they define a diffeomorphism current.
Exactly.
On the global, and this diff current, maybe you can do that maybe next week, is been studied by Gramshore back again in the paper in 1988, and it's an interesting to find this to see what this diff current is doing. Could it be related to the covariant? Could be related to the total derivative term of the dilettante? I don't know. I maybe at some point I'm not speculating. I'm probably saying something wrong online. So let me stop there. But we don't know. We don't know.
Okay. Well, but I mean, it is interesting because it ties back to everything else we do. Like if we try to imagine what a calculation that would give us a result like 2.4 would look like. Again, 2.3 is set essentially by convention. We know what operator, the format is trace t equals beta I expectation value of OI plus R2 times C function, right? That's kind of we have some of these beta function terms and we have the R2 term. Okay, great. Now, what could possibly look
like this?
Yeah, yeah, exactly, right? No, so how does one compute these forgetting anything about local RG? Well, we did that too, right? We briefly went over the derivation involving the background field expansion of the sigma model, where we expanded the fundamental fields are like coordinate fields. We already at that point can assume we have a degree of covariance to be able to use a normal coordinate expansion, right? And in so doing, we discovered that the leading corrections involve curvatures, and that's why we get the one loop coefficient ending up in the alpha prime expansion, ending up looking like a Ricci term. And then we're going to have a two loop coefficient where you have two of those Ricci terms, the two of the Riemann terms, and so you're going to have Riemann squared, so on and so forth. So already at that stage, we're doing this normal coordinate expansion with the assumption that we have the general coordinate invariance operating in the background. Or what is that general coordinate invariance? It's some kind of like field redefinition invariance. That's where it's going into. It's a question of simultaneously shifting G versus shifting X, right? Like It's the play between these two things, right? And similarly with phi. And so what's happening here is that, look, beta mu nu is like a beta function for g, right? So it's dg dt. Now g under diffeomorphism shifts exactly in the format of what's going on with beta mu nu. All you're doing is passing d over dt through the rule for a diffeomorphism of the metric, an infinitesimal diffeomorphism of the metric. And what's left to do is figure out how to filter everything coming from the calculation where you commit to some RG scheme, commit to some regularization, how to filter that into 2.4, right? So even without knowing anything, I should be able to write 2.4 and 2.5 down. Maybe not explicitly what mu is, but I should be able to do that just from knowing that I have this filter definition in my pocket, right?
Yeah.
I can write
Yeah.
2.3 to
I think
2.5.
that's correct.
Yeah. So like all that is already just in the pocket. Then it's a question of doing, like, committing to some regularization, doing the calculations. Sorry, take 2.1, do the background field expansion, do the calculation, but then see how to filter everything into the format that is given by 2.3, knowing that we have the invariances given by the first two lines of 2.4. And that's essentially how one would derive all of these results. Then, of course, I mean, you have to be very
Yes.
careful.
Yes.
Make sure you get the coefficients right, but that's kind of like, just to say that otherwise it just seems very mysterious. I mean, it always did before I tried to sit down and do this. It seemed very mysterious. Like, why does everything conspire into these very nice shapes? Why does everything take such a nice form? The reason is that there's this underlying field definition invariance baked into the formalism, right? Just
Absolutely.
from, yeah.
It's always there. It's always the secretly doing these what appears to be magical, right? It's this RG scheme figure redefinition thing. And really everything comes down to that. Whether they are local or non-local field
Right.
redefinitions. So that's important because
Yes.
it's important that probably all the field redefinitions we're talking about here, they're not all local. Probably the involved non-local field redefinitions um, as well. But yes, the paper, the reference, of course, the original reference 10 and 11, but reference 19, especially in 15 and 20, where the explicit form of WU and has been worked out is interesting to look into and
For sure.
understand. But there's lots and lots of technical details here. But yes, that's the essence, the central point is what we wanted to point out. Exactly. And what else? So one thing I wanted to one other point is that why and why, as pointed out by Zetlin, the formulation of a C theorem, Alazimologicov, for two-dimensional quantum field theories. They're not sigma models. They're not really string theory sigma models sort of fail. And the reason is interesting. If you were so because we've been explaining this here, these are what we have explained before. Hopefully they're familiar. This is the gradient. So the action is S, phi I and phi j denotes couplings. So basically what we're saying is that the gradient of the action, effective off-shell action S with respect to a coupling phi I is proportional to the beta function, right?
Just to hop back for a second, we should say that, like, what is being referred to here, the D conditions between this many functions, blah 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 blah.
Go through the D condition. Wow.
All that comes from just the Wess-Zumino consistency conditions for the local RG equation above 2.4. So, like, if you scroll up a little bit, you get to 2.12. That's just, again, from 2 episodes ago, the Wess-Zumino consistency conditions applied to this specific 2.3 local RG equation. That's what's being referred to here as a
you're specifically referring to 212, right?
Yeah. That's what's being referred to here as a non-renormalization of the trace of the Angevin momentum tensor. And
Yeah.
the idea is that that, in effect, is an integrability condition solved for by 2.13, right? Those are the
Right.
relations that, like, in some sense, if you wanted to satisfy this, you need 2.13 to be satisfied with Kij being non-degenerate, right? That's like the only
Yes.
condition here, and that really matters.
Absolutely. And I think these are known by derived by Corsi and Tofuti. I think these are known the Corsi-Tofuti relations, and they're or consistency conditions, if you will. And we have a very nice extension of the Corsi-Tofuti relation, something I've never really discussed before or presented in my talks because it gets too technical.
Yeah.
Is that we have this Corsi-Tofuti relationships in our equation of motion section on paper, where we actually extend this to non-linear order. This
Nice.
is linear order, and the function will be extended to non-linear order, and we show something really cool. Um, um, about the beta functions of the dilaton and the beta functions of other couplings. Um, but I just wanted to hint that this is a very important and nice relationship that we use and
Yes.
extend. And we find something very interesting in the paper that maybe we'll come to at some point and explain, because it's really interesting. And for the sake of well, I'll say that offline. Don't say that
Sure,
here.
sure,
But
yeah.
okay, so yes, as Vasu pointed out, and the part that I did not want to, I basically neglected, is that 213 are is basically required, right, as a consistency condition or solution to 212.
Yes.
And 212 is a consistency condition. It's important. It's an integrability condition, and if you keep it there, then that implies that there must be a covariant action. This covariant action is an off-shield action in target space, for which the gradient of must be the beta functions, the beta functions that go into 212. So that 213 comes from 212. So there's a hint here also, Vasu, about that the effective action, off-shell effective action that we have just been describing, for which that appears to have the beta functions as its equation of motion, it is not something that randomly appears out of nowhere, right?
Exactly.
For example, equation 212, because this is what we see, for example, in Polchinski, right? We see there's this effective action that has the beta functions as its equation of motion, but we're never told how to get this effective action from the target space, right? And that's why
Exactly.
I said at the beginning that in this formalism it tells you in a very systematic way how to get the effective action. How does it appear from the worldsheet? It's not just appears out of nothing, right? Or out of and here's a hint that this 212, for example, tells you that there should be a covariant action in target space whose gradient is proportional to the beta functions, where the proportionality factor happens to be nothing but our beloved RG
Yes.
Samologikov metric
Yes. Yes. Yes.
on RG space, KRG, which we refer to as G, but now because we're using capital G, uppercase G, to denote space-time metric, we're using Samologikov's metric as kappa ij.
Yes. Yes.
So this is the content of 212, that there's an existence of that there should be or exists an action, covariant action in target space, whose gradient is proportional to the beta functions. And the proportionality factor happens to be this Samologikov metric, which is another non-degenerate, important covariant operator. Okay, nice. And here's another identity: the diff invariance of the you see, covariance or the diff invariance in target space always constraining, right? Always puts constraints on you. It's nice, right? And that's why we always keep it, and implies this. Nice. Okay.
Right.
And this relates beta G, and this is another important point that will become maybe the beta function of the graviton, which is beta g, and the beta function of the dilaton, beta phi, are related by equation 214, and in fact, even 212.
Yes, yes.
And even something that is important is that, in a sense, you can express always the beta function of the dilaton in terms of the beta function of the graviton, right? So one of them is less fundamental than the
Right.
other, in if you like. And this is basically the content of 212 and 214, equations 212 and 214. And I can express one beta function via the other, right? And that's important. Maybe just keep that in mind. Maybe it will come, will appear later. But here's the action. This is easy. Okay, fine. To first order of alpha prime. Again, we're working here to first order alpha prime. Here's an action that you find in Polchinski.
Yes.
In the chapter 6, that has the beta functions of the g and the phi as equations of motion.
Yep.
Amazing. Comes from some consistency conditions on the world sheet. But it's important because we do not want to forget that we're doing here the C theorem. What's important here to note is that if you work out the kappa ij,
Yes.
so this is an explicit workout of what the Somolovchikov metric is, and at least in this sigma model string theory context, right? This is what we have been saying, that this is the positive definite. And if you remember, let me restate it for like the 5th time. The reason that the Somolovchikov C theorem in 2 dimensions work, right, is that when the beta functions vanish at fixed points, we say that the gradient is going to be 0. When the gradient of the C function is 0, this implies that we're sitting at an extremum, and the statement is only valid because of the positive definiteness of the Somolovchikov metric.
Yes.
Otherwise, everything will break down. Yes. But this is exactly what happens here.
Unfortunately, it's not positive definite.
It's not positive definite. It's not positive definite. The kappa ij in the string theory context with a dilaton and a curved well sheet, here's the 218 and 290, it is not positive definite. And therefore, the formulation of a 2-dimensional C theorem for string theory in the sigma model, for sigma models, fails because of the sign indefiniteness of kappa ij. This is Somolovchikov metric. And this is important, very, very important. And here's what it's explicitly said. U does not have a sign since the metric is not sign definite.
Right.
So then why? The reason is what's going on. And as we point out, Ed and I point out in part 1 of our paper, that I think in section 6, that the reason when we work out the 2-point correlation function with a cutoff on the sphere, we found this discrepancy between the sign of the 2-point function of 2 primaries and the two marginal primaries, and 2 primaries which are called non-curvature, which we call non-minimal couplings. And the reason is this, well, we explain it later.
Yes.
This sign indefiniteness is a sign of the conformal mode problem in quantum gravity. And you might think, oh, what's going on? Yes, this has to do with the square root of G modes, and which is the source of this conformal mode problem in Euclidean quantum gravity, which I know you know a lot more than I do about. But this is how string theory sort of reproduces for us.
That's utterly fascinating. Yeah,
and this is a fascinating thing, that this sign indefiniteness is related to that. So in a sense, if you want to solve the conformal mode problem, Or it is, a Lorentzian signature, whatever you do there, you'll have to solve this problem of finding out a consistency theorem on the sphere for
Yes.
two-dimensional sigma model.
Yes, yes, yes. There's no, yeah. I
Um,
mean, the solution to one is the solution to the other.
I think so. So that's the point. And then the other part of the story is how this whole thing is related to the sphere partition function, which is this back, but I'm not gonna get into that. But how, which is off-shell string theory. How is that related to the sphere partition function by virtue of these equations? This is maybe next time,
Yes.
because so far we've been isolating the local RG and C theorem part from the off shell, but this is all related and all is going to become important, absolutely important, when we relate this part of the story to the sphere path integral and the off shell action. But what we haven't covered yet maybe is the Perelman's entropy, how to
Right.
construct a monotonic RG flow, Ricci flow, because it's just the
The
first
leading
order
term, yeah.
RG flow, Ricci flow, and Perelman's entropy using constraints, which again we discussed in the paper in different ways, but maybe we'll get into that next time.
Yeah.
Is
Yeah, that would be
is
really
is
nice. We
is
could even
how the
open up
status.
you could even open up Perlman's original paper and just see, and as sort of something that I commented on, which was that it's remarkable to see that he had, despite being a mathematician, he had a deep appreciation for the physical manifestation of this exact question. And there's
Yes.
a very nice passage in that paper where he goes through just a sort of intuitive understanding of why it needs to be that if this was to be thought of as an RG flow, that there has to be a gradient property associated to it. Like if you didn't have the gradient property, if you had a limit cycle, then he goes
Yeah.
through
You have a limit
very
cycle.
weird,
Exactly.
yeah, very weird effects you would see. So we can go through that next time. So next time we can go through the entropy functional. So basically circumventing the conformal mode issue, the entropy functional, and the spheres, right? So really getting into the off-shell string theory
The
as
sphere partition function and
yeah,
the
the
off-shell
sphere
string.
partition function. But this was great. So we've managed to now
Mm-hmm.
really sort of bring the Sigma models under the umbrella of the local RG and then see what the issues are having to do with the curve background, the vanishing central charge, and the non-positive definiteness of the Zamolodchikov metric. So it's yeah, wonderful. And it had to be that way if C had to be related to the space-time action. If we're
Mm-hmm.
in Euclidean signature, how could we not see the conformal mode problem? That just comes from the fact that there's this bilinear form you get by taking the variations. We just looked at the pure two derivative part of the variation of the Einstein-Hilbert action. There's just gonna be a structure there that's not positive definite. That's just a fact. Can't get away from that. So just the requirement that all these things need to be the same will force us to have this issue. Like in some sense, one should have almost seen this coming. And indeed, it does come. So
Yeah.
should plant a flag there. So no, this was
Absolutely.
wonderful. Yeah, this is really good.
Thank
I
you.
feel like
Of course. I
we've
mean, my
really
pleasure. Yeah, yeah. It's something that maybe I can hear stop share.
well thank you so much, Amr. I think that this has
No,
been
absolutely, my pleasure. It's been always pleasure to kind of engage in it, explain and learn as we go along. So
yeah, no,
it's been
and I
very
think that
fast.
there's just so many jumping off points, and again, the fact that this has gotten a little bit forgotten is a bit of a shame, but it's great to sort of bring the focus back to these issues because there's just these old problems that we haven't made much of a dent in collectively. If you think
Yeah.
about even like conformal mode problem, don't know that much more than we did all that time ago. RG flows, the Sigma models, we don't know all that much more than we did all that time ago. Maybe we have some higher loop calculations in perturbation theory for beta functions
Yeah.
and so
Yeah.
on, but
Yeah.
like there's just these
That's
deep
what we do.
conceptual issues we just don't know, and it's very important. And so it's great to see that you and Aaron have been focusing on some of these issues and bringing it again and again. When we get to part two of your paper, we could even talk about the relation to Susskind-Uglin prescription and black hole
Yes.
entropy.
Yes. Now we get into holography and the modern
Yeah,
day development.
Exactly. So no, I think that this is great. I'm very glad that you chose the vehicle of my podcast to to
Absolutely.
talk
I'm
about
happy.
this.
I'm happy. It's my pleasure. It's my pleasure.
It's great, and indeed we will be back because there's more to talk about. Absolutely.
More to come. Absolutely.
So yeah,
Absolutely. It's my pleasure. Yes, we definitely do.
if you made it this far, feel free to like, subscribe, share, and comment. This is Theoretically Podcasting, and I will catch you next week.